right, Stat Nation. This is chapter 5, day 3, probability. Let me share my screen. Probability is the single most requested thing for me to repeat to kids. It's kind of elusive. Kids or people understand it for a while, then they forget. And so I've decided to record quite a few of these because I think it'll be the best, especially as we get closer toward the AP test. All right, so this is the beginning of the notes, chapter 5, day 3. Now, a couple things. I teach probability very slowly, and I try to be very thorough because I give a lot of practice and a lot of thinking. So you're going to want to stop this video a lot and process the information as much as you can. All right, so probability. We're going to go over 3 rules and 3 key phrases, okay? So probability is basically, and this is a fraction here, it is the number of outcomes that you're looking for in A divided by all of them. Some people use this fraction. They use desired on top, and all on the bottom, what you're looking for, okay? So an event is a collection of outcomes. A trial is a single run. And of course, the outcome is the observed result. No problem there, okay? Some real basics about a probability. A probability can't be negative, even though you might think to yourself, Mr. Snyder, the idea of somebody thinking you're handsome has a negative probability. It's actually not true. The worst I can be is 0. So that's the good news for me, okay? And you can't have a probability over 100%. You can have over 100% improvement, things like that, but not in sheer probabilities, okay? The sum of all probabilities is 1. This formula, this is the summation symbol, and P is the probability, and E sub I is every individual outcome. So if you add them all up, you get 1, okay? And the complement, not compliment, like Mr. Snyder, you're so handsome, not that kind of compliment, but complement is 1 minus the probability of that event. And then E to the C power is how you say the complement of an event, all right? Now, there are 3 very, very key phrases in probability. And believe it or not, in this particular day, I'm going to introduce these, but we're not going to do them a whole lot today. I'm setting it up for future days because I'm still going to be working on combinations and permutations today. But I want to introduce a few concepts so you see it more than once. You'll see it today. We'll get away from it a little bit, and then it'll come back in subsequent days. But at least you'll seen it a couple times. And I'm going to do some examples on the screen here while we do this, okay? There are 3 crucial phrases in this chapter: independence, mutually exclusive, and conditional probability. Independence means you can multiply. It has to do with one event not affecting another event. Mutually exclusive has to do with adding things together, okay? And if things are mutually exclusive, they can't happen at the same time, and we'll talk about that, okay? And then there's conditional probability. That means when the conditions change. This reads B given A occurs. And I have that here. Look at it like this, as B over A. Look at this line as the fraction line. Okay, now I'm going to give you an example of each one of these. Well, you might stop this and write this down. And again, I'm going to go through this. We're going to get away from it, but I need you to see it more than one day, okay? So, intersection. This symbol is the intersection. It means where they both happen at the same time, okay? So let's think of two independent events, okay? And then this is related to this. Let's think of two independent events. The probability of me having two boys in a row in a family, two in a row, okay? Now, one pregnancy does not affect the other pregnancy. So because they're independent, the probability of having a boy in the first child is a half, and the probability of having a boy in the second child is also a half. So a half times a half is 1/4, okay? And the multiplication works because the events are independent. Now, sometimes events are not independent, so you cannot multiply. How would you know that? Sometimes we'll be proving that events are independent or not independent. I'll show you that later. And sometimes they tell you that the events are independent, meaning you can multiply, okay? So another example of independent events, let's say in a baseball team, the first batter has a batting average of 333, okay? And the second batter has a batting average of 400. Oh, I got a little big there. I'll move that over here. Okay, the second one has a batting average of 400, okay? 0.400. If you consider the first batter and the second batter independent versus the pitcher, then the probability of them both getting a hit would be 0.333 times 0.400. Okay, that's independence. All right, pretty easy idea. Okay, mutually exclusive. This literally means can't happen at the same time. Please write this word down too. It shares this with disjoint, which of course I have written down right there, disjoint, okay? Now, this is the general addition rule right here, okay? If you're wondering one or the other, and this means union, and this means or, okay? So if we are trying to figure out the probability of one event or the other event, this is how you would do it. Let's say the probability of me getting a hit in baseball is 30%, and the person batting behind me has a chance of getting a 40% getting a hit, and someone asks you, what are the chances that one or the other gets a hit? One or the other. Well, we would know that you're going to add those two. However, we have to subtract where they both happen at the same time. And that would be, in this case, their product if they're independent events. Okay, so the answer would be 0.3 plus 0.4 minus 0.12, which is 0.58. Okay, so that's in baseball. One or the other getting a hit, where the first batter has a 30% chance of getting a hit, the second batter has a 40% chance of getting a hit, and you consider their at-bats independent. So the product would be where they overlap. Notice this is the intersection. This is where they both happen at the same time. A great example of intersection would be in a Venn diagram, this area right there. Okay, we're going to show you all of these skills over time. I'm just introducing it today. Now, if someone were to say in this same problem, there's a 30% chance of first person getting hit and a 40% chance of the other one getting hit, and these two events cannot happen at the same time, okay, then you'd be subtracting 0. Sometimes the Venn diagrams don't cross, so that number is 0, okay? So let me give you just some insight on what this part of the equation could be, okay? A intersection B could be their product if the events are independent. A intersection B could be 0 if the events are mutually exclusive or can't happen at the same time. And A intersection B could be some given number if they are not independent, but also not mutually exclusive. That's a crazy word. Not mutually exclusive means they can happen at the same time. It's a double negative. That's pretty tough. All right. So look at what I've done so far. This is a very, very hard concepts to explain. So I introduced them today. We'll get back to them in the next section, but I want you just to see it once. Okay. For right now, the multiplication rule. You can multiply event A times event B if the events are independent. And you would be getting their intersection, which is that upside down symbol right there. Okay. The rule for adding one or the other is you add one, you add the other, and you subtract out where their overlap is. And their overlap is that part of the Venn diagram. Now, where is that overlap? That overlap is either their product, if they're independent. It's 0 if they're mutually exclusive. And it's some other given number if it's neither mutually exclusive nor independent. So let me give you an example where this would be 0. Okay, I'm going to slide down here now. Okay, where would this be 0? How about this? If you're rolling a die, what's the probability of getting a 3 or a 4 on a single die? A 3 or a 4? No problem. A 3 is 1/6. Or means add. A 4 is 1/6. And you can't get a 3 and a 4 at the same time on one die. Those two events are considered mutually exclusive or disjoint. So the answer is 2/6. Okay, sound good? Now, let's talk about 2 dice. 2 dice. 2 dice. What's the probability of getting a 6 or doubles if you're rolling 2 dice? All right. So how many ways can we get a 6? I believe there are 5 ways to get a 6 out of 36 possible rolls. Okay. Now, how did I get 36? 2 dice, 6 times 6, 36. That's from lesson 1. Okay. So how did I get the 5? Okay, I'm going to slide down here. You can get a 1 and a 5 and a 1, a 2 and a 4, a 4 and a 2, and you can get a 3 and a 3. Just hold on a second, moving things around here. You can get a, like I said, a 3 and a 3. Okay, so there's the 5 ways. Doubles. I think you realize that there are 6 doubles. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Now, we double counted something. There is an intersection between 6s and doubles. I'm going to circle it. That's the 3, 3. It makes a 6 and it makes a double. So so this is going to be adding this. 536 plus 636 minus one of those rolls because there is an intersection. Okay, so that's how you would solve that problem. All right, so we're going to get back to all that fairly soon. Conditional probability, which you see listed down here, that is going to be where you have a new denominator, not the total on that. And we're going to see these 3 concepts constantly. If I was you, I would take a highlighter and I would highlight that, highlight independence, and those are the 3 big, gigantic concepts in this chapter. They take time and we will do a great job of it. I'm just introducing it today. Hopefully you get this information down. You listened and learned a little bit. Now we're going to back up a little bit, and we're going to be doing some of the OR rules, addition rule and multiplication rules here. Okay, with probability. And so you can copy all this stuff down if you'd like. And we are going to work on these simple probability problems, and we're going to do them from several different perspectives. So we're going to get away from what we just got done talking about and go into this, because I want more experience on this right now before we move forward. And then the next time you see that stuff, you'll be a lot better off. Okay. So, and I'm going to do this multiple ways, not just one way. I have all the combination theorem written out here to make so that way it's the longest way to do it. There's other ways to do them too. So let's try it. Okay, 2A. All right, 14 people are playing Mafia. Well, one person, not you, is the Mafia. What is the probability you catch the Mafia on the first try? Well, obviously, if there's 13 other people, the answer is simply 1/13. Now, the combination way, by the way, this is the denominator, right, would be I have to choose of the 14 people, I got to choose the right person. And then of the other 13, I choose none of them. Nobody would do it this way. Everybody would just do 1/13. I can't even imagine someone going through combination theory doing it that way. But it is a way you can do it. Okay. And then on the second one here, after 3 unsuccessful rounds, what is the probability you will catch the Mafia on the next one? Well, the answer is clearly 1/10. There's 13 people to choose from. After 3 are done, it's going to be 1/10. That's pretty obvious, okay? But I have the combination theory written out. Nobody would do it that way. But I'm just letting you know it's there, okay? 2B. Here's a couple cool ways to do this, okay? 3 of your 18 coworkers are spies. We know what that's like. Get those coworkers that are talking to the boss. Okay, anyhow, you interrogate 3 of your colleagues. Interrogate's a strong word. You talk to them. What is the probability you interrogated all 3 spies? All right, here's a couple ways to do this. The way that I chose to write it out is using combination theory. Okay, and again, stop your video at any time. Write these out, walk yourself through them. You are responsible for trying to understand this, okay? So I did, of the 3 people I interviewed, I got all 3. Of the 15 people I didn't, none of them were spies. And then I'm dividing by the denominator, which is 18 people, and I chose 3 of them. To me, there's an easier way to do this. The easier way to me would be, all right, so I went 3 for 3. That means I have a 3/18 chance of interrogating the first one. Then there's 2 left out of 17 I'm going to multiply. Then it's 1 out of 16. To me, that's the easier way to do this. It makes a lot more sense. Okay? All right, so that's 2B. Now, sub double I down here, this is a fairly key phrase. We do at least one a lot in this class. It shows up a lot. It seems to be tested quite a bit. I got a little break there. It seems to be tested quite a bit, okay? At least one spy. What's the probability that you interrogated at least one spy? I look at least one. Again, if you want to go through this combination way to do it, absolutely feel free to do it. This would be at least one means that I got 1, or I got 2, or I got 3. Now, getting 1 would mean of the 3, I got 1, times 15 of the ones that I didn't get, I didn't choose, 2 of them were not spies. Plus, at least 1 means this is 1, or 2, or 3, okay? At least 1. And this is, of the 3 people I talked to, I got 2, times 15 that I didn't talk to, there was 1 that was a spy. And then the last one is, of the 3 I talked to, I got all 3 spies, times 15 of them, and I got none of them. Divided by the denominator will be 18, choose 3. Now, I think the better way to do at least one is 1 minus none of them, okay? This is a key concept. At least 1 is 1 minus none. I'd write that down. And I'm going to show you how to do it differently, okay? So what are the chances I didn't get any spies? Well, 15 of them aren't spies. So I'm going to go 15 over 18 minus the second person I talked to. I only have 14 left that were not spies and 17 total. So I'm going to multiply, not minus, multiply, times 13 of the 16. Okay. So that's going to give me the probability of getting none of them. And if I go 1 minus that, 1 minus none is at least 1. That's a really cool way to do that. Okay? So try that. That'll match up to this answer down here as well. Okay. Next. There are 10 cards, 4 of which are winners. 4 of which are winners. You pull 3 cards. You win the grand prize if all your cards are winners. What is the probability you won the grand prize? All right. Here's the combination way of doing it. Of the four cards, I got 3 of them. Okay. And of the 6 cards I didn't want, I got none of those. And I'm dividing it by the 10 cards total where I chose 3. Okay. Another way to do this would be to say, all right, 4/10 chance on the first try of getting a card I want. Okay. Once I get that card, there's only a 3/9 chance next. Once I get that one, there's only a 2/8 chance next. That's going to be the same answer. Notice these are really factorials, because these are dependent events, because you're not replacing. So you end up with a countdown: 10, 9, 8, 4, 3, 2. They're factorials. So from our previous lesson, this is 4 permutation 3, the first 3 of 4 factorial, divided by 10p3. Nobody's going to do it that way. Nobody's going to think of that. This just makes sense to me. Okay? All right. Now, the next one is a little bit harder. You win some prize if you get at least 2 winners. At least 2 means 2 or 3 winners. That's actually kind of tricky to do. 2 or 3 winners. I'm going to stick with this way. So this would mean 4 choose 2, because I have 4 cards and I got 2 winners, and then I got 1 non-winner, plus, because at least 2 means 2 or 3, and or means plus. This is 4 choose 3 times 6 choose 0 divided by the 10 cards I have, divided by 3. Okay. Look, these are not heavily tested items. They are not. But I think it's important that we spend some time just playing with probability, just so you get a handle on it. Okay. I will be very, very specific as we go on this chapter what is going to be tested upon, and you'll be fine. Okay. But I think it's important to make videos of these so that you guys can see these. You can repeat them, because often people need me to repeat this in class all the time, and it can be very hard. Okay. So let's go to the next one. Okay. We got a bunch more to do here. This is going to be really cool. Okay. So an item D. Okay. Given 6 objects in a group and 14 objects in group B, group A and B, you randomly pick 4 from both groups. Find the chances that you pick all 4 from group A. Okay. All right. All from group A. No problem. Okay. So, couple of ways to do this. All right. 6 in an object in A and 14 in B. What are the chances that you pick them all from group A? Well, you could do this way. This is fine. This is 6 choose 4, because of the 6 objects that you have, all 4 of them came from group A, times 14 choose 0. By the way, that's 1. Okay. Divided by 20 choose 4, because we had 20 total objects and we chose 4. Now, to me, the easier way and more logical way to do this would be to do the following. Okay, there are 6 objects in group A, so I got a 6/20th chance of getting it, the first one. And here we go again, the countdown. 5/19 times 4/18 times 5/6/5/4 times 3/17. That's it, right here. that will give you the same answer, because that is 4 consecutive objects from group A. And of course, you're not replacing it any time. So you have a countdown in the numerator of how many objects came from A and a countdown in the denominator from how many objects came from B. Okay, no problem. Now, the same thing's going to happen here in picking all from group B. You can walk yourself through this, no problem. Picking them all from B is going to be, there are 14 in B, so 14 20ths times 13 19ths times 12 18ths times 11 17ths. Those are all 4 from group B. And again, you can see the combinatorial way of doing that, or you can see the way they do it in terms of permutations. Pretty cool, okay? All right, the last one, you cannot, it's really, really difficult to do the permutation way, picking 2 from A and 2 from B. You can see it, okay? 2 from A means 6 of those from A and you chose 2, times 14 of them from B and you choose 2, divided by total of 20 objects and you're choosing 4, okay? So there's that one. All right, 2E now. Given 8 objects in group A and 7 in group B, you randomly pick 6 objects from both groups. No problem. Picking them all from group B. All right. All from group B means you pick none from group A and you pick 6 of the 7 from group B divided by 15, choose 6. Or I would probably do it this way. And at this point, I've been doing this so much, I think I got the handle on this. I'm going to say, all right, so 6 objects, group B, I'm going to go 7 permutation 6 because it's the first 6 of 7 factorial divided by 15 permutation 6. Okay, that will also give you the same answer. This is really cool. Okay, now does this pop up a lot in AP Stats? No, but it pops up just enough, and there's just enough concepts here, and there's a mindset that we got to have that we're going to be able to handle any probability question that it's worth putting a few days into. Okay, picking 4 from A and 2 from B. All right, we got this. 4 from A, 8 choose 4, 2 from B, 7 choose B, okay? And then divided by the 15 total, choose 6. Awesome. And then picking at least 4 from group A, at least 4. At least 4 means getting 4, you can underline it, 4 or 5 or 6, okay? And I'm going to let that one stand for itself. I'm not going to go into too much detail on that one. Okay, last one over here on this set. You got 3 objects from A, 5 in B, and 4 in C. You randomly pick 3 objects from all groups, picking 1 from each group. No problem, 1 from each group, okay? So 1 from each group would be, you got 3 choose 3 objects in A, you got 1 of them. 5 in B, you get 1 of them. 4 in C, you get 1 of them. And the denominator is you got 12 total and you're choosing 3 of them, okay? And this is all calculator work. It would be, that's in less than 1. You really wouldn't do that by hand or anything, or I wouldn't anyways. You could, I suppose. Okay, picking at least 2 from group B, at least 2. Okay, you have a familiar denominator. At least 2 means 2 or 3. 2 or 3. So picking 2 means of the 5 in group B, you picked 2, and of the 7 remaining objects, you got 1. And then you go, or of the 5 in group B, you got 3 of them, and of the 7 remaining, you got none, because there's only 3. There's only let's see here. Yeah, 2 or at least 2. Okay. All right, because you're going to be picking 3 objects. Okay. Last one. None from group C. None from group C. Whoops, here we go. Okay. None from group C means, shouldn't have moved that. Let me try to get there. Okay, none from group C means there's 4 objects and you got none of them, times the 8 remaining and you picked all 3 of those, divided by 12C3. That stands for itself. Pretty simple. Okay. Move myself here. All right. Similar idea. G, given 5 objects in group A, 4 in B, 8 in C, you randomly pick 5 objects from all groups. What are the chances you pick all 5 from group B? Okay. Well, the answer, of course, to that one is a tricky question. It is 0 because there's only 4 objects in B, so that's not going to happen. Okay. Now, picking 2 from A, 1 from B, and 2 from C. Okay, we've done this a million times already, so you can kind of walk yourself through that one, I hope. And then at least 3 means 3 or picking 3 or more, okay? You're going to pick 5 objects, so picking at least 3, which means 3 or 4 or 5. Okay, and your denominator is going to be 17, choose 5 times 19, choose 6. Okay. All right, so I'm going to go ahead and just leave this up for, I'm going to center this and leave this, okay? And I'm going to do some differentiating here. Hopefully you can walk yourself through the rest of these, okay? Try to walk yourself through the rest of these guys. And it really is overkill. I've done a lot of problems on this, okay? And then pause it here is what I would recommend and walk yourself through it. And then once you're done, I'm going to go to the craps deal there down here, okay? So craps is really fun. I really like this. We're going to end up playing this in class, but for right now, I'm just going to explain it here, okay? So craps is played with 2 dice. And you guys probably know, let me lower this a little bit. You guys probably know, seen this if you're ever in Vegas or Reno or whatever, those big tables where they roll 2 dice on it, okay? Now, we're going to talk about how you play. The game is played, and I have the rules of the game. It's about the first roll and subsequent rolls. The game can last 1 roll, or the game can last 2 rolls, or the game can last an infinite number of rolls. And the games can go pretty quick. You can play 4 games in 1 minute. You can play, it can go really fast. That's why it's called the alligator pit, because you can lose your arm real quick, a lot of money. All right, so here's how it works. If the first roll is a 7 or an 11, you automatically win, okay? 7 or an 11. Okay, so here it is, 7 and 11. I have all the combinations down there. So the chances of you winning right away is 8 out of 36, right away, because you can get a 7 or an 11, and there's 8 ways to do that, okay? Now, if you get a 2, a 3, or a 12, okay, you lose right away and the game's over. Those are called the crap rolls, okay? So those are the ones that are losers right away. Now, if you get these 4, 5, 6, 8, 9, 10, those are called a point, okay? And if you get those, the game changes, okay? So at first, the 7 is your friend, okay? And then it turns on you. So this is what we got. If you roll a 7 or an 11, let me clear this. If you roll a 7 or an 11, get a cool color here. If you roll a 7, you win. There's a 6 out of 36 chance you win right away. Or an 11, you would win right away, okay? Now, if you get these, the game changes. And conditional probability, which we introduced earlier in the day, starts taking over. Conditional probability. All right, this is what happens. If you get one of these numbers, then the only number that matters is rolling your number that you got again or a 7. I'll give you an example. Let's say you roll a 4 on your first roll. Then you have to get a 4 before a 7. And the 7 becomes evil. Okay, 4 before a 7. Okay, got it? I'm putting in parentheses for some reason, or quotes for some reason. 4 before a 7. Okay. Now, if you get a 7, you lose. If you get a 4, you win. Any other number doesn't matter. Just roll again. So it can take a while. Okay. So let me talk about that again. Okay. So I'm going to rewrite it for the third time. Let's say you get on the first roll, you get a 7. 6 out of 36 chance you win. Or you could roll an 11 right away. 2 out of 36 chance and you win right away. Now, there's 6 other ways to win. The 6 other ways are you get a 4, then a 4 before a 7. Or you get a 5 and then a 5 before a 7. Or you get a 6 and then a 6 before a 7 on subsequent rolls, etc. Okay? So the 7 is your friend in the first roll. But once you have a point number, which is called a 4, 5, 6, 8, 9, 10, it becomes your enemy. So what are the chances of winning if you get a 4? If you get a 4, I'm circling it right down there. There is a 3. You have a 3 out of 36 chance of getting a 4. But you have to do something in addition to win. And means times. And you have to get a 4, and there's 3 of those before you get a 7. Now, why did I write a 9 down? Because the only rolls that matter are the 4 and the 7. That's the only 2 rolls that matter. And the 4 and the 7, if you add them up, there are 9 total rolls, because we are doing conditional probability, conditional, where the conditions have changed. All 36 rolls don't matter once you establish a point. It doesn't matter. Only those 9 matter. Cool. Okay. I'm going to change colors again here. Or you could get a 5, or means plus. You could get a 5, which is, 5, there are 4 of those. 4 out of 36 chance. And you got to get a 5 before a 7. There are 4 of those, and there are 10 total of the 4s and the 7s. Cool. Or you could get a 6, and there are 5 ways to get a 6, as you can see here. And you got to get a 6 before a 7, which is an 11 right down here. Okay? Because there are 6 7s. All right. Change colors again here. Or I'm going to do the 8, 9, 10 now. Or you can get an 8, which is a 5 out of 36 chance, and an 8 before an 11. Notice I'm saying one number and writing another. This is high skill. Okay. Or a 9, which is a 4 out of 36 chance, and a 9 before an 11. Or you could get a 10, 3 out of 36, and a 10 before an 11. 10 before a 7, 10 before a 7. That's crazy. This is the probability of winning in craps. It's really cool if you write that out. Now I'm going to slide down. Probability of winning in craps, it ends up being 0.4929. Check that out. It's almost 50% chance of winning. It's real close. Right here, 0.4929 chance of winning, okay? So if winning is 0.4929, then losing would be 0.5071, because it's a complement. And it's about a 1.5% house advantage. That's it. Pretty cool. Now we're going to play this, and we're going to see what our probability of winning is, okay? Just in our sample, okay? Pretty cool. So that is chapter 5, day 3. Lots of days in this chapter. And again, I introduced some concepts that we're going to really dive into later. And then I got into craps a little bit. So good luck on those. Don't be too worried about all the combinations and permutations. I'm going to be minimizing those in the test, okay? But again, we're playing with them, getting your mind ready for probability, etc. All right, talk to you soon.